Hi, I'm Max Humes, and today I'll be teaching you about direct current, or DC for short, circuits. From Ohm's laws to combining resistors, we have a lot to get through in this lesson, so let's get started. To begin, let's look at what a circuit even is. Imagine a stream of water flowing down a mountain. Water starting at the top of the mountain is at high gravitational potential and moves down the mountain to a lower gravitational potential. Water flowing down a mountain is analogous to the way that electric charge can flow through a conducting wire given an electric potential difference. However, you might be thinking, how does the water get to the top of the mountain in the first place? Building onto our original mountain, we can imagine that the water is flowing into a sort of elevator. This elevator moves water at the bottom to a higher gravitational potential, much like a battery in a DC circuit uses chemical reactions to provide a way for electrons to flow from its negative terminal to its positive terminal, which is at lower voltage. Remember, work must be done as electrons want to move from low to high potential. A battery's symbol is in a circuit diagram is two or more bars like this, where the positive terminal is the longer of the lines and the negative is the shorter one. When electrons are given a path from one terminal of a battery to the other using a wire, electrons will begin to flow through our circuit, creating what we call current. The quantity current, denoted by the capital letter I, can be thought of as the amount of charge measured in coulombs that moves through a cross-section of wire in a single second and is measured in amperes. The equation to calculate the average current over a period of time is I equals Q divided by T, where Q is the charge that moves through the cross-section, and T is the time that it takes for it to do so. For example, if we find that 3 coulombs of charge move through a cross-section of wire in 0.5 seconds, we can calculate the current by dividing the charge that passed through the cross-section by the time that it took to do so, giving us 6 amperes of current. Unfortunately, many years ago, when Benjamin Franklin experimented with electricity, he believed that the current was the flow of positive charges instead of negative charges or electrons like it actually is. Because of this, while electrons are really flowing from the negative terminal to the positive terminal of the battery, the conventional direction of the current is from the positive terminal of the battery to the negative terminal of the battery. In a simple DC circuit, the energy of the flowing electrons must be dissipated over what is called a resistor. In a DC circuit diagram, a resistor is shown as a squiggly line through a piece of wire. A resistor resists the flow of charge to regulate the current in a circuit, and the amount of resistance in a resistor, or how much it impedes the flow of electrons, is measured in what we like to call ohms. When current passes through a resistor, the voltage drops. So for instance here, if the current is moving in the direction of the arrow, voltage of A has to be greater than the voltage at B. When a single resistor is connected to a single battery, the voltage drop across the resistor is equal to the electric potential difference between the terminals of the battery. Other cases are a little bit more tricky, but we'll get into that later. When a circuit is created with no resistors, the only resistance in the circuit is extremely small resistance in the wire itself, causing the current to flow at alarmingly high rates, which can cause the wires and the battery to heat up or even be destroyed. This is called a short circuit. Lucky enough for us, while the resistance in a circuit is constant, the voltage, current, and resistance in a circuit are all associated through one simple equation called Ohm's law. This law states that the voltage drop across a resistor is equal to the current times the resistance and can be rearranged to solve for all three quantities discussed before given the other two. Let's go through some examples really quick. In this circuit, we are given that the resistance of the resistor is 4 ohms and that the current in the circuit is 1 ampere, and are asked to solve for the voltage across the battery. Using Ohm's law, we find that the voltage drop across the resistor, and therefore the voltage of the battery, is equal to 4 ohms times 1 amp, or 4 volts. Next, we are given the same simple circuit, but are now given that the voltage of the battery is 9 volts and the current in the circuit is 4 amperes, and are asked to solve for the resistance of our resistor. By rearranging our equation to solve for resistance, we see that the resistance of our resistor is equal to 9 volts over 4 amperes, or 2.25 ohms. Now that we have the basics down, we can move on to solving more complicated resistor circuits. When we have more than one resistor in a circuit, we can solve for quantities in the circuit, such as current, by first simplifying the circuit into one equivalent resistor and working backwards from there. To find the equivalent resistance of two resistors which are directly connected to one another, also known as resistors in series, we simply add all of the resistances together. For example, the equivalent resistor of two resistors with resistance 20 ohms and 40 ohms will simply be added together to create a resistance with REQ, or equivalent resistance, of 60 ohms. When resistors are in series, the current across each resistor is the same, and the voltages add together to create the voltage drop across this equivalent resistor. Going back to our example from before, let's say that our 20 ohm resistor and our 40 ohm resistor are connected to a 5 volt power source. And we want to find the voltage drop across resistor 1 and resistor 2. First, we can go back to our 60 ohm equivalent resistor down here and redraw our circuit with only this 60 ohm resistor and our 5 volt battery. Here we can find the current that will be through both of these, as it's equal to the current in the equivalent resistor. So we can rearrange Ohm's law to get I equals the voltage over resistance, or 5 over 60 amps, which simplifies, or not necessarily simplifies, but can be written in decimal form as 0.083 repeating amps. Given that our current in both of these two resistors, by working our way back up, is 0.083 amps, we can now find the voltage drop by using our handy-dandy V equals IR equation and plugging in for our first one, 20 and 5/60ths, which is 0.167 repeating volts. And then we can plug in 40 and 5/60 for the current, and get 3.3 volts. Next, in the case that current is given two directions in which to flow, our resistors are considered to be in parallel. To find the equivalent resistance of resistors that are in parallel, we use the equation For example, given that these two resistors have a resistance of both 13 ohms and 28 ohms, by plugging our two fractions into a calculator, we find that 1 over REQ equals 1/13 plus 1/28, which is equal to approximately 0.113. And to find our final REQ, all we have to do is take the inverse of that number. You can use the x to the -1 key on a standard TI-84 graphing calculator, and we get a total resistance of REQ equals 8.88 ohms. For resistors in parallel, the voltage drop across each resistor is the same and equal to the voltage of the power source. So let's say this is 9 volts. Then this will have 9 volts, and this will have 9 volts. For resistors in parallel, the voltage drop across each resistor is the same and equal to the voltage drop across its equivalent resistor. So for example, if this battery was 9 volts, then the voltage drop across both this resistor and this resistor would be 9 volts. Unfortunately, due to time constraints, we can't do too much more problem solving, but we're going to do one simple example of everything that we've learned, bringing everything together with this simple circuit. So we're going to be trying to find the voltage drops across resistor 1, resistor 2, and resistor 3 here. So first, to do this, we're going to rewrite our circuit with an equivalent resistor of 300 ohms, simplified using our law before, just by adding the two resistances. And we still have our 400 ohm resistor down here. Now, with this circuit, we already have the voltage drop across resistor 3, which is right here. So that's going to be 18 volts. But now, in order to get the voltage drops across both of these resistors, we have to work our way backwards. So first we're going to find the current across this resistor here. So in order to do that, we're going to use Ohm's law, and we can rearrange so that we get I is equal to the voltage over the resistance. And our voltage is 18 volts over 300 ohms, which gives us a total current of 0.06 amps. Now, given this current, we can simply use Ohm's law to find the voltage up here by putting in 0.06 as our current and our first resistance of 100, giving us 6 volts across resistor 1, and 0.06 times 200 ohms, giving us 12 volts across our second resistor. Alright guys, I'd like to thank you for joining me in this video. It's been a pleasure teaching you about some of the most important rules in DC circuits. We couldn't cover things like capacitors or more complicated resistor circuits as there were time constraints. The video is getting a little bit too long, but thanks for watching, and I'll see you around.